Okay, so picking up kind of where we left off last time with this puzzle. Um, this is the beginning of chapter 5. So all the stuff that we do in chapter 5 is applications of the uniqueness of prime factorization. So here, this puzzle I mentioned yesterday. So the main part of the puzzle is we're being asked to find an age. So 2/3 of the square of this integer that's meant to be an age is a cube. That was the hint that we had, and so we had shown this proposition that might as well, it's on the same page. So if k is an integer and m is a positive integer, if m is m's a kth power if and only if all the exponents in the prime factorization are multiples of k. Okay, that was the thing that's going to make doing this puzzle a lot easier. So we have 2/3 of 2/3 times the square of some age. So if a is the age, and we have prime factorized a as the following thing, and so on, then 2/3 times a squared is, as we saw, so this is 2 times So let's square a, so all these get 2, multiplying each of these exponents. So this is 2 to the 2a, 3 to the 2b, 5 to the 2c, and so on. Multiplying by 2, I get an extra copy, so I get an extra plus 1 in the exponent of 2, and I get minus 1 in the exponent of 3. So what I get here is 2 to the 2a plus 1 times 3 to the 2b minus 1 times 5 to the 2c times 7 to the 2d, and so on, right? None of the other exponents change at all. Okay, using this fact that I'd proven, that so I claim this thing is equal to something cubed, right? So this is equal to something cubed. All right, but this, by the theorem, I can't remember what this theorem is called, or, okay, it's called a proposition in the textbook. So by proposition 5.1, this implies that 3 divides 2a plus 1, and also 3 divides 2b minus 1, and also 3 divides 2c, and 3 divides 2d, and so on, right? So every single exponent in the prime factorization of this thing must be divisible by 3, right? So all exponents are multiples of 3. Okay. So, this is, I could already come up with some solution here. So knowing that these have to be multiples of 3, I could just mess around with these numbers. So for instance, I could take C, D, E, and so on to all be 0, and then I could just make this work for A and B. So if you take A equals 1, so that this is 3, so 3 divides 3, and B equals, say, 2, so that both of these are 3, and the rest are 0, then what do I get, right? So note, note taking A equals 1, B equals 2, and C equals D equals E, and so on, equals 0, this yields my age to be 2 to the first 3 squared times 5 to the 0, 7 to the 0, and so on. So this is 2 times 9, so this is 18. Looking at the puzzle again, this definitely works. It's supposed to be a young lady, so this works perfectly fine. But we can actually see what the general solution to this thing is, so that we get all possible ages that satisfy this, not just the smallest one, okay, which this one is. All right, so then using this fact, how do I solve this in general? Well, note, I have a list. Maybe I'll bring that list back so I don't have to rewrite it. So I have this list here. So what does this mean? Well, if 3 divides 2a plus 1, well, 2a plus 1 is odd, right? So, and it's a multiple of 3. So this implies that 2a plus 1 is 3 times like 2j plus 1. But this, if you solve for a here, then this means that a is like 3j plus 1 for some j. Okay. And just going down the line, 3 divides 2b minus 1. Well, again, 2b minus 1 is odd and divisible by 3. So that means that 2b minus 1 is equal to 3 times, say, 2k plus 1, which, solving for b, means that b is equal to like 3k plus 2 for some k. Okay. And just continuing to go down the list here. So 3 divides 2c. What does that mean? Well, this is an even number, but the idea here is I want to use this proposition that I had coming from chapter 2, that I know something about 3 and 2, and that's that their GCD is 1. So if 3 divides 2c, well, 3 is also, smaller than, or sorry, 3 is larger than 2. So GCD of 2 and 3 are 1. And so what do I get? What do I get here? Well, no, that's the reason why. So this means that 3 divides c, and the reason why it divides c is that the GCD of 2 and 3 is 1. So remember, if you have two relatively prime integers, then if 3 divides the other integer, or sorry, if that integer divides the other integer times another, it means that that thing that it's relatively prime to doesn't contribute to its divisibility, so it has to divide the other thing. So this is one of those propositions we proved at the end of chapter 2. So c is actually a multiple of 3. The same thing is true for all of these, right? So again, because GCD of 2 and 3 is 1, and that's true all the way. All right, and so as a result of that, c is equal to 3 times like c prime for some integer c prime. D is equal to 3 times d prime for some d prime, and so on. All right. Okay, so now we're able to write out what the generic age has to be. So using all these facts, I can write out that A is, just writing out my original notation here. So there's A prime factorized. Okay. But then using each of these things that I've now boxed. So here I can peel off one copy of 2, and the rest is a multiple of 3. I can peel off 2 copies of 3, and what's left is as an exponent is a multiple of 3, and then the rest of these are multiples of 3, period. So what this means is that I can write this as 2 to the first times 3 squared times what's left is 2 to the 3j times 3 to the 3k times 5. C is 3 times c prime, so this is 5 to the 3c prime times 7 to the 3d prime, and so on. The rest of these are all powers of 3 is the idea. And so this is 18 times something here cubed, right? So times 2j times 3k times 5c prime times 7d prime, and all that is cubed. So written more simply, this is 18 times b cubed. Okay. All right, so the age is 18 times some integer cubed, and we're going to get a different solution to this for every choice of integer here. So b equals 1 implies that a is 18. That's the one we found easily by setting a equals 1, b equals 2, and the rest of these exponents 0. So what is the next possible option? So the next possible option is if b is equal to 2. So a is 18 times 8, which is 144. So the next possible age that satisfies the limerick is 144. So if you wanted to rewrite the limerick to get an answer other than 18, you'd have to say something about the person being really old, right? Of course, you could keep going here, and they're just going to be massively older. So maybe you would have to pick out exactly how old you're okay with here. Okay. So this is an example of how to use prime factorization. Really, the purpose here was not that particular limerick. It was just to see how you might use this fact that knowing that an integer is some kth power means that you know something about its exponents, namely that they have to be a multiple of k. All right. So that's that. Now, so the next application of unique factorization concerns proofs concerning irrationality. So these were some of the first actual math proofs that you did concerning like the irrationality of square root of 2, square root of 3, stuff like that. So just quickly, a number that is a real number is rational if it can be expressed as a ratio of two integers. Right, a over b. And of course, you could do a better job actually defining the set of rationals, saying that it's just the set of fractions like this where b is not 0. So we say we denote the rationals with q. So when I want to talk about the rationals as a set, I'll use that notation. Then an irrational is just any real number that's not rational. So an irrational number is a real number, say r, such that r is just not in the set of rational numbers. So it's just not rational. Okay. Of course, like I said, I could define Q to be the set of fractions a over b with the understanding that I want to list out fractions that are in lowest terms here. So the GCD of a and b is 1. And I could say that, it's technically you're putting an equivalence relation here where these are the same, if they have the same reduce. So two given rational numbers are the same rational number if their lowest term, if in lowest terms it's just, some a over b. So I could define, my set Q to be just the list of these fractions in lowest terms with the understanding that I have this equivalence relation that equates fractions that have the same expression in lowest terms. So So that's one thing that I could do. That set, it turns out, is of course the same set as the set of real numbers that have decimal expansions that eventually become periodic, meaning they have some pattern, right? They start repeating after a certain point. I'm not going to talk about that yet because it's not going to be that useful to us right now. The problem with thinking of irrationality and rationality in terms of repeating decimal expansions is that it's not. So, of course, there's an algorithm for computing. You can compute a repeating decimal expansion to a rational number. You might have seen that before. So there's a process by which you can do this. But thinking about irrationality in terms of repeating decimals, or in the case of irrationality, like if a number is going to be irrational, then if I've said that every rational number has a periodic decimal expansion, then that means that necessarily any irrational number can never have a periodic decimal expansion, meaning that there can be no repetition. It can't become periodic eventually. So if it's going to be irrational, then it has to have a decimal expansion that never has this periodicity. But the problem is that that's a really, really terrible type of way to characterize irrationality, because how would you show that a number is irrational? How would you ever do that with that definition? Because you could compute 5 trillion digits of an irrational or of a number you think is irrational, and even if it was not periodic after those 5 trillion digits, obviously what happens if the periodicity starts at the 5 trillion and the 5 trillion and first decimal spot. So yeah, it's a bad way of thinking about irrationality. So kind of the classical way of thinking about irrationality first, like the most basic thing, is to use the power of contradiction and assume that the thing that you're talking about is rational, and then come up with some reason why that can't be the case. So the absolute classic proof, which I'll repeat here, well, I haven't even stated it, so I'll repeat here just for completion's sake. Here's the theorem. Square root of 2 is irrational. You already know this proof probably by heart at this point, but just in case you don't, here's a quick refresher. So suppose that square root of 2 is rational. Right? So suppose that it is rational, i.e. square root of 2 is equal to a over b for a and b in the integers, b not 0. And let's assume that we've put this fraction in lowest terms, so GCD of a and b is 1. Okay? So this is a quick way of getting what we want. All right, so it is in lowest terms. Maybe I'll write that out here. So AB is in lowest terms. That's, as I mentioned before, that's kind of one of the first places GCD practically pops up, is in talking about fractions in lowest terms. Okay, so what does this mean? Well, I look at this, I square both sides and multiply both sides of this equation by b squared. So this implies that 2 is equal to a squared over b squared, which implies that 2b squared is equal to a squared. Okay. Now, here uses a fact that you can convince yourself of really quickly. A squared is 2 times b squared. So a squared is 2 times some integer, so a squared is even, right? So this implies a squared is even. This is also one of these really early things you prove in a proof course. Well, if a squared is even, that means that a has to be even. Okay. But if a is even, that means that a is equal to, say, 2k for some k. That's an integer. Okay. All right. Of course, we can assume that these are all positive integers if you like. But anyway, so if a is even, it's equal to 2k for some positive integer k. And so what do I get? What do I get when I plug this into this statement? Well, this means that 2b squared is equal to 2k squared, which is 4 times k squared. Dividing by 2, what do I get here? I get that b squared is equal to 2 times k squared, which means that b squared is even, which means that b is even, i.e. b is equal to 2l for some integer l. Okay, but I've got a contradiction here. Why do I have a contradiction? Then GCD of A and B is not 1. It's at least 2. So that's a contradiction. It's at least 2 because I've shown that both of these are even. Right? And if you have two even integers, their GCD is at least 2. Right, so it's certainly not 1, but I assume that their GCD is 1. I assume that this fraction is in lowest terms. So practically speaking, right, if you're trying to intuitively see what is the problem here, it means that if square root of 2 were rational, then it would be expressible as some fraction that could never be reduced, right? No matter how much you reduce it, you end up with this fraction. So even if you took both of these things and divided by 2, you would end up with some, k over L here. You could do the same thing over and over again, right? So this k over L would also be reducible by factoring out a 2, and so on. You could just go on forever. Okay. All right, so that's the classical proof that square root of 2 is irrational. All right. So there's going to be, so the textbook is going to list like, I think 3 or 4 other ways of proving this. I'll mention one of those ways later in passing, but if you want to have a look at those, this is 5.2.1. So 5.2.1 gives 4 more proofs of this fact. So there, of course, there's more than just that, but just to give an idea for other ways of proving this, and I'm going to talk about yet another way of showing this here in a second, using what's called the rational root theorem. We'll do another quick proof of this, but before I do that, I wanted to talk about a quick generalization of this fact. So you're asked oftentimes in an early proof course to prove, the irrationality of some numbers involving radicals other than 2, so square root of 3, square root of 5, and so on. So you might say, well, which of those are actually irrational, right? How do I know that square root of some number is irrational? So the answer is the following. So let k be greater than or equal to 2 and k be an integer. So let n be a positive integer that is not a perfect kth power. Then the kth root of n is irrational. So this tells you more than the question I asked. I asked, when do you know that the square root of something is irrational? Well, whenever it's not a perfect square. The square root of something that is not a perfect square is going to be irrational according to this theorem. But more than that, the cubed root of something that's not a perfect cube is going to be irrational. The fourth root of something that's not a perfect fourth power is going to be irrational, and so on. Okay. So how's the proof of this go? Again, we're in chapter 5, so that means that in some form this comes from unique factorization of into products of primes. So prime factorization is what does it. How do I do this? Well, we prove the equivalent statement. Remember, irrational is defined in a negative way, meaning that something is irrational if it is not rational, right? So look at the contrapositive of this statement. So this is if the kth root of n is not rational, so if it's rational, then n is a perfect kth power, right? So I'm negating this not as well. So the equivalent statement is if the kth root of n is rational, so if this thing is actually rational, then necessarily n is a perfect kth power. This is what we prove. You didn't have to phrase it this way. I phrased it this way because the textbook did. You could have just as well, proceeded by contradiction, and it would have been slightly awkwardly worded if you did that, but it's not a problem. So you could have proceeded by contradiction and obtained the contradiction that we're going to get as a proof of this thing that I've underlined. Okay, so suppose that this thing is rational, right? The kth root of n is rational, i.e. the kth root of n is equal to a over b, where a and b are integers, and we can say that they're positive and b is non-zero, right? Okay. In case we're confused about whether or not this includes 0. Okay. So, doing that, similar to my proof that the square root of 2 is irrational, if I raise both sides of the kth power, what do I get here? I get n times, after I've multiplied, b to the k is equal to a to the k. Okay. Well, write n and b using their prime factorization. So say that we've done that, and n is 2 to the x sub 1 times, x sub 2. I don't want to keep track of which prime I'm at, times 3 to the x sub 3 times 5 to the x sub 5, and so on. And that looks like a u, kind of. This is an n. And b, similarly, is like a 2 to the z sub 2 times 3 to the z sub 3 times 5 to the z sub 5, and so on. Okay. Well, then, and of course these, so x sub p, z sub p are non-negative. Then n times b to the k is equal to, so each of these exponents is going to be x sub 2 plus k times z sub 2, x sub 3 plus k times z sub 3, and so on. So this is 2 to the x sub 2 plus k times z sub 2 times 3 times x sub 3, or to the x sub 3 plus k times z sub 3 times 5 to the x sub 5 plus k times z sub 5, and so on. Okay. But this is equal to a to the k. So whatever this is, it's a perfect kth power. But if that's going to be the case, this proposition I had that helped me solve the puzzle at the beginning of chapter 5 tells me that each of these exponents has to be divisible by what? So by the earlier proposition, each exponent must be divisible by k, right? Each exponent's a multiple of k, so every exponent here must be divisible by k. So what this means is that x sub p plus k times z sub p must be equal to k times some y sub p for all p. Okay. Well, what's that mean? So this means I could actually subtract k times z sub p from both sides. So what I get is that x sub p is equal to k times y sub p minus z sub p, i.e. x sub p is a multiple of k for all p. But x sub p, those are just the exponents in n. So again, by the earlier proposition, n is a perfect power of k, or perfect kth power, since each of its exponents is a multiple of k. And that does it. Okay. So we started out with the assumption that that the kth root of n is rational. We got this expression, n times b to the k is equal to a to the k, using the prime factorization together with this fact that if you know that some integer is a perfect kth power, then k has to divide every single exponent, right? So every single exponent has to be a multiple of k. And so that just spits it out immediately, again, using that proposition. So because this is an if and only if statement, so you're going in one direction here and we're going the backwards direction here, right? So an integer is a kth power if and only if every exponent in its prime factorization is a multiple of k. All right. So this is nice. Makes your life a lot easier if you're wanting to come up with some proof for your students to do when it comes to irrationality. So what does this imply? So here's some examples. Of course, square root of 3. Let's do the 7th root of 16. Just writing down the examples in the textbook. But of course, cubed root of 5. How about the 4th root of 13? That's another pretty good one. These are all irrational. And I don't need to prove that specifically for these expressions. I can actually just state this theorem. Okay. Of course, if you wanted to see an explicit proof of these things using, these numbers, what could you do? Well, of course, you could just sub these numbers into the proof that you did, and you get the proof that you're looking for. So anyway, so that's another application of prime factorization. So if you want to have a look at other proofs, as I said, this is in the subsection 5.2.1, pages 79 through 81, I think, does it. So pages, so note, pages 79 through 81 in the textbook contains more proofs of irrationality of square root of 2. So proving something in multiple ways can help get some insight into why something is true. So and sometimes it's just fun to try to prove that, you know, to try to prove some fact. Especially there's a book that's kind of like a joke math book. It's called, I think it was, I can't remember when it was written, either the 70s or 80s or something. It's called Mathematics Made Difficult. And the purpose of the textbook is to write the most convoluted proofs possible. So even like, you know, it has a proof that like 2 is prime in it that takes like multiple sentences to prove. And of course, like extra points are awarded if you use, you know, some really advanced machinery to prove some really basic, like almost obvious fact. So it's a pretty funny book because you know, it's another type of game you could play is try to prove some really simple fact using nothing except some really advanced machinery and nothing that ends up being circular or too stupid, but yeah, trying to prove some advanced or some really elementary fact with something mega advanced is always a fun thing as well. Okay, so the next application of the prime factorization of integers is and its uniqueness is the rational root theorem. And this might come as somewhat of a surprise because looking at it on its surface, maybe you don't see exactly how it's related to unique factorization, but you'll see once you see the proof. The proof is actually pretty straightforward. So what is the rational root theorem? Well, you've seen this in some form before because it gives you an efficient way of guessing, or not really guessing, but listing out all of what the rational roots of some given polynomial with integer coefficients has to be, like what the only possibilities are. So what does this theorem say? So let p of x be a polynomial that's degree n. So it looks like this, plus a sub 1 x plus a naught with integer coefficients. So be a polynomial with integer coefficients. So a couple of things, and this will be true for the remainder of the course, whether I write it or not. What does it mean when I say integer coefficients? So one, it means that each of these coefficients a sub I are in the integers, obviously. But also, just the fact that I've written the polynomial in this form, because I don't want to have to keep rewriting, when I say that a polynomial has degree n, I mean this leading coefficient's not 0. So a sub n is not 0, and we'll say that a sub 0 is also not 0 in this application. So that's not always going to be true that we're going to say that, but in this particular application, we want a sub 0 to not be 0, because if it were 0, if the constant term is 0, then there's a common factor of x here I could pull out, and so one rational root in that case would be 0. So the idea is that I want to use this, you know, ideally I'm using this when just looking at the polynomial I don't have any idea about any necessarily too obvious roots, right? So if the constant term is 0, this would put me in the case where it's obvious what one root of this polynomial is. I want to be out of that case. I want to be looking at a polynomial that I can't just immediately say, oh yeah, it's got 0 as a root. Okay. So here we go. So this is what I'm assuming. All right. Now, here's the main statement. If R, which is written as a U over V, is a rational number, and again, we'll say that U and V, or this fraction is in lowest terms, so their GCD is 1. So with GCD of U and V equal to 1. Okay, and P of U over V, or P of R, is equal to 0. Right. Then U divides the constant term, A naught, and V divides the leading term, A sub n. Okay. Now you might have seen this expressed in various forms. You might have seen the actual list show up here. This is equivalent to any other form of this you've seen, and I'll show you. I'll do an example after that shows. It's all you do is you say, all right, if U divides the constant term, that gives you a list of possibilities for what U could be, because you just list out the divisors of A naught, and you list out the divisors of the leading term, A sub n, and then you form this fraction for every possible combination, right? That's what's going on here in some other statements of this that you might see. All right. So looking at this statement again, it's not immediately clear why this would have anything to do with prime factorizations or how this even works. In fact, after you even see the proof, it might not be immediately clear how this is related to prime factorization, since the proof actually doesn't explicitly use prime factorizations. But what it does is it uses a fact that was proven directly from this fact coming from the extended Euclidean algorithm that you get, that you can express GCD as linear combination of A and B. And that, of course, was the fact that was really what got you the prime factorization in the first place. So in a sense, this theorem is not necessarily proven directly with prime factorization. It is like they share a common ancestor. Like this proof has a common ancestor with the fundamental theorem of arithmetic. Okay. So anyway, how does this work before I do an example here? All right. So I have polynomial, degree n. There it is written there. And I'm assuming that I have a rational number in lowest terms that is a root of this. Okay. So, well, if it's a root of this, so P of U over V equals 0, that implies, just plugging that in directly to the polynomial, this implies that A sub n times U over V to the n plus A sub n minus 1 times U over V to the n minus 1, and so on, plus ... plus A sub 1 times U over V plus A naught is equal to 0, right? Okay. So what I am going to do is I am going to multiply both sides of this equation by V to the n to clear denominators. So multiply by V to the n to clear denominators. And when I do that, what do I get? So in this first term, I get A sub n times U to the n plus the next thing I get is A sub n minus 1 times U to the n minus 1, and I've multiplied by one extra copy of V here, so this is V. And so on, all the way down to A sub 1 U, and here I've multiplied by an extra n minus 1 copies of v. So v to the n minus 1 plus a naught v to the n is equal to 0. Okay. All right, so this is the expression that's going to do all the work for us. Okay. How is it going to do that? So there's a couple of facts I'm going to note. So one, right, note that all of these terms, except the first one, are multiples of v. So all terms except a sub n u to the n are multiples of v. Right? There's a copy of v in every single one of these other terms except the first. So all terms except the leading term are multiples of v. What does that mean? Since this expression is equal to 0, I can simply move all those other terms to the other side of this equation. And what I get is a sub n u to the n is equal to some linear combination of terms where v is present in every single term. Right? So I get a sub n u to the n is equal to some expression that, some linear combination where v is in v is in every single term. So it's a linear combination of v times something, okay, in every single term. And so what this means is that v divides a sub n u to the n. But there was a key assumption I made here that is going to do a lot of work, which is the assumption that the GCD of u and v is 1. If the GCD of u and v is 1, v dividing a sub n u to the n implies that v divides a sub n. Okay, and that is because the GCD of u and v is 1. Okay, so I get that v must divide the leading coefficient. Similarly, looking at the same expression, every single term here involves a u except the constant term. So all terms except a naught v to the n are multiples of u. You see where I'm going with this already. So this implies that u divides a naught v to the n. But if u divides this product a naught v to the n, then u divides a naught for the same reason, since the GCD of u and v is 1. And that's it. That's exactly what I wanted. So rational root theorem has a very quick proof. All right, there it is. Let's see how to apply this, right? And then it may come rushing back to you how you applied this in the past. So let's look at an example. Let's see. Let p of x be 2x cubed minus 5x squared plus x plus 3. Okay, so I look at this thing and I say, all right, just looking at it directly and thinking for 2 seconds, I don't really see an obvious root of this thing. What are the possible rational roots? Now, it's important, right, that looking at the rational root theorem, it says absolutely nothing about like raw existence, meaning it doesn't say anything about whether a rational root for the given polynomial exists. You know already that one might not exist. Given some polynomial with integer coefficients, there's absolutely no reason to expect that it has any rational roots. Okay, so what this does merely is list the full list of possible rational roots. So what you're really saying is if the polynomial in question had rational roots, or had a single rational root even, it would have to be in that list. Right? That's what That's what you're saying. Of course, nothing in the list might work. That could happen, but you're listing out all the possible rational roots. Maybe 0 of them work. Maybe all of them work. Okay, this is the idea here. Okay. All right. So, how does this? And you might even think to yourself, like, come up with a quick example. Doesn't have to be too hard. You can come up with degree 2 or better example of a polynomial, such that all of the entire list you get here works. You can come up with a quick example. I'm confident. So, what are the possible rational roots? So, the possible rational roots are as follows. So, how do I do this? So, I know that I'm looking for u over v. All right, I'm looking for u over v such that u divides the constant term. So, u divides 3 in this case, and v divides 2. Okay. All right, so u divides 3, the constant term. V divides the leading coefficient, 2. So what are the possibilities of u here? So u could be 1, could be 3, right? These are prime, so my job is easy in a sense. But remember, I'm looking for all rational roots, so there's no reason to exclude the negative ones. And so here, if I'm thinking of divisors of 3, I don't just have to think about the positive ones. I'm thinking about the negative ones as well. So there, right? This is, here I'm not thinking about, just strict divisibility. I'm kind of cooking this in here to what comes next. You don't have to do this. In fact, if you like, right, if you don't like thinking about these as divisors, since we usually restrict our attention to just positive integers, you can say u is 1 or 3, since 3 is prime. Similarly, v is 1 or 2. And then when I form the fraction u over v, I'm looking at, plus minus u over v. So I don't want to toss out the negative things here. So whether you cook them in here or not, it doesn't matter at all. What are the possible rational roots? The idea is that I form u over v for every possible combination here. So for instance, 3 over 1, 1 over 1, right? Those are formed here. So I get plus minus 1, right? So that's 1 over 1 and minus 1 over 1. I get plus minus 3, so that's 3 over 1 and minus 3 over 1. I get plus minus 1/2, so 1 over 2 and minus 1 over 2. And lastly, plus minus 3/2, so 3 over 2 and minus 3 over 2. So there are 8 possible rational roots. You can check a few of them. You'll see that I don't think any of them work except one. So checking a few, we find that P of 3/2 actually works. Okay, doesn't have to work. You don't have to find a single one, right? All of these could fail, but in this case, we have found a rational root. Okay. So obviously this works out a lot better for the polynomials in question. And again, check out, I could have done this. I could have given you a polynomial that was a 4th or 5th degree polynomial. But if the constant term, the leading coefficient, were small enough, then there's still not a whole lot of these factors I have to worry about. So my fractions u over v, there's just not that many of them. So if there's not that many of them, there's not that many I have to check. It's a lot quicker, obviously, if those numbers are not too big, meaning that these u, and there's not that many possibilities for u and v. Also, even if they are big, right? If the numbers in question are prime, then there's less possibilities for u and v, right? So if you have some prime leading coefficients or constant coefficients, then the amount of divisors, right, possible divisors, is obviously restricted here. So that's another good way of making good use of this. So the textbook gives an example of when you could use the rational root theorem even when there's like a lot of factors, so that you end up having a ton of possible rational roots. If you're smart, in a lot of cases, you can actually reduce the number of rational roots that you have to check, because if you just list out this entire list, in general, if you have many possibilities for u and v, some of the fractions in the list are actually going to be repeated. So the list could be really, really long, but it's actually maybe not nearly as long because a lot of those fractions are repeated. They're not reduced, something like that. Okay. So anyway, that's one thing. Another thing, note, the rational root theorem immediately gives us a proof that square root of 2 is irrational. So, note, square root of 2 is irrational. Just a reminder, right? And quick proof of this, well, square root of 2, so if square root of 2 is rational, then there exists a rational number r such that r is equal to square root of 2, but then r is a root of the polynomial p of x, which is x squared minus 2. All right. But by the rational root theorem, the only rational roots of p of x that are possible are, let's think about this, the leading coefficient is 1 and the constant coefficient is minus 2. So leading coefficient 1, that means that v if I'm thinking of r as u over v, v is only allowed to be 1, so every denominator is 1, right? And so the only possibilities are the divisors of 2 or minus 2, so plus minus 1 plus minus 2. Plus minus 1 and plus minus 2. All right, these are the only rational roots that are possible. Okay, but r isn't any of those. So r is not equal to plus minus 1 or plus minus 2. So that's a contradiction. All right, so if it were rational, then it would be a root of this polynomial. But this polynomial only has 4 possible rational roots, and none of those are actually roots, right? So you might say, wait, well, like, how do I know that square root of 2 is none of these, right? Well, none of these work. None of these are roots, right? None of these are roots of p. Okay, so phrased in another way, forgetting about trying to do this by contradiction or anything, just look at this polynomial p. Its only possible rational roots are plus minus 1 and plus minus 2. None of those work. You just plug them in and none of them work. Since none of them work, it has no rational roots. So if you've identified a number that if it were rational, it would have to be a root of this thing, well, then that number can't be rational, right? Okay. In fact, you can adapt this whole process of using the rational root theorem to prove that other fact, the more general fact about an integer n that's not a perfect kth power, the kth root of that thing being irrational. So in fact, can also use rational root theorem. I'm not going to write it out. So you can also use rational root theorem to prove that n not kth power implies the kth root of n is irrational. Okay. The polynomial you look at, I'm not going to write it out, but the polynomial you look at in this case is x to the k minus n. That's what you look at. Look at x to the k minus n. If n is not a perfect kth power, well then it's not a root of this thing, right? So if you want to prove that equivalent statement that if it is a perfect kth power, it is a root of this thing, you can just look at the potential rational roots and find that you're not going to get what you want, right? Or that you're going to get exactly what you want. So that if this is rational, then it must be a perfect kth power. That's another way of saying it. Okay. All right. So, and the last thing I wanted to do here today. Well, maybe I might get a chance to do the Riemann Zeta stuff, because if I don't do the proof of the Pythagorean triple stuff, which I didn't plan on anyway because it's really long, so I'll state the theorem, but I'm not going to prove it. I'll leave that. I will leave that as something that you can read on your own. So when this course has been taught in the past, usually I think the proof of this is skipped. So last application before moving on to the Riemann zeta function. So Pythagorean triples. So what's a Pythagorean triple? So a Pythagorean triple is a solution to a squared plus b squared equals c squared, an integer solution. So a triple ABC of positive integers that satisfies a squared plus b squared is equal to c squared is called a Pythagorean triple. So how many Pythagorean triples are there? Well, it was known since antiquity that there were infinitely many of these. I'll talk about a method for generating these. In particular, we're interested in a particular type of Pythagorean triple. So if the GCD of all three of these, so you might want to remind yourself what it means to discuss the GCD of more than two things, right? So it generalizes in the normal way. So a common divisor of three things is no different than a common divisor of two things. It's just now you have an extra number to consider in the set. Again, it's always a non-empty set, so you can talk about the greatest element. So that's what the GCD of three numbers is. If the GCD of these things is 1, so if those three things are relatively prime, then what does this mean? Then we say that ABC is a primitive Pythagorean triple. Okay. Note, might have thought about this immediately. If the GCD of a triple is equal to D, then the GCD of that triple divided by D is equal to 1. Okay. And think about it. If A, B, C is a Pythagorean triple, is A over D, B over D, C over D a Pythagorean triple? The answer is yes. Okay, so this is the This is the way this works. If you know that one of these is a Pythagorean triple, you get a primitive triple by dividing by their GCD. So there's a question. So are there infinitely many, we'll say primitive Pythagorean triples, even though this previous note means that this primitive bit is not holding us back too much. Are there infinitely many primitive Pythagorean triples? I'll spoil the fun and say yes. The answer is yes. Secondary follow-up question is there a way of generating all of them? Okay, and the answer to that question is also yes, although like I said, I'm not really going to go through the proof of it. Okay. All right, so this is central question of this little discussion. Okay, so there's one way that is an easy way of generating Pythagorean triples. It doesn't generate all of them, but it will generate infinitely many doing this. So you can generate infinitely many with this process, but it doesn't hit all of them. So here's one quick example of how I can hit a bunch. So take, say, an odd number. So I'm just going to take 9 here. Take an odd number, square it. So 9 squared is equal to 81. Okay. Second, split it such that, split it in such a way that you have a difference of 1. That might not make a lot of sense stated like that. What do I mean? 81 is 40 plus 41. If you take an odd number and square it, you can always do this, and we'll see why in a second. It's not too complicated. But if you take an odd number, square it, split it like this, you're always guaranteed to be able to split it in such a way. And it turns out that if you do this, the end result is a Pythagorean triple if you take the smaller thing here. So it turns out the end result is a Pythagorean triple. 9 squared plus 40 squared is equal to 41 squared, which is pretty neat, right? And you can check that yourself if you don't believe it. So 3, the end result is a triple. Well, it's a Pythagorean triple. So 9 squared plus 40 squared is equal to 41 squared. Okay. And not just any Pythagorean triple. Actually, I get a primitive one. It's primitive. Why is it primitive? What's an easy way of seeing that? It is primitive because the last 2 entries in the triple differ by 1. Right? They differ by 1. Their GCD is 1. So the GCD of the triple is 1. Right? The GCD of this triple 9, 40, 41 is 1. So that's interesting. Okay, and that always works. So this generates infinitely many primitive Pythagorean triples in this way. Okay, so that's one way of doing it. Another way of doing it, before I go into why this actually works, maybe I should do why it works, so why this works. Okay, so we said that we were going to take an odd number and square it. So what did we do here? So we took the number 2n plus 1 and we squared it. Okay, so odd number squared gives us, just expanding this is 4n squared plus 4m plus 1. So I said that I could split it as number plus another number where I only have 1 as the difference. So yeah, I can do that easily. This is 2n squared plus 2n plus 2n squared plus 2n plus 1. Okay. Then 2n plus 1, 2n squared plus 2n, and 2n squared plus 2n plus 1 are a primitive Pythagorean triple. And the reason why is you can check the identity, which is that 2n plus 1 squared plus 2n squared plus 2n all squared is equal to 2n squared plus 2n plus 1 all squared. So check that yourself to actually make sure that this works, but that's why it works. That's how the algebra works out. Okay. So another way, before I give the general statement, so another way in which this can be done is instead start with a multiple of 4. So start with a multiple of 4. So let's say 8. Okay, over here. So square it. So 8 squared is 64. Okay. The idea is to take 1/4 of this square and subtract 1 and add 1. So 2, take 1/4 of the square and subtract 1 and add 1. This is going to give me 2 numbers. Okay, so 1/4 times 8 squared minus 1, well, that's 15. And 1/4 times 8 squared plus 1 is 17. Okay. And this yields a primitive Pythagorean triple. In this case, it's 8, 15, and 17. So, questions about why this is primitive. Okay, so let's think. The last 2 entries are odd, and they differ by 2. So they're odd and they differ by 2, so their GCD is 1, so the triple has GCD 1. Okay. So we're done yet again. In fact, you could do this process actually starting with any even integer, not just a multiple of 4. But you don't always get a primitive one in that case. Sometimes you get an even thing, so you'd have to divide by 2 at least once to get a primitive thing. So this, starting with a multiple of 4, just makes this process always spit out a primitive, and I don't need an extra step where I divide by its GCD. Okay. So notice that you are going to, so for instance, you doing it this way, you end up with a triple that wouldn't have been generated in this first method, right? So the first method would not have hit this triple, for instance. So neither of these give the exhaustive thing that generates all of them. So for that, I want to state the following theorem. So theorem, but we can actually describe how any Pythagorean triple is generated, a primitive even, so any primitive Pythagorean triple is generated. So this is going to hit everything. So this is the main theorem in this section. So let A, B, C be a primitive Pythagorean triple. Okay. Then C is odd. Note that statement does not have to be true if it's not a primitive Pythagorean triple. Okay, and you can quickly come up with an example. Just take a Pythagorean triple and scale it, right? So so this does not have to be the case at all if you don't have a primitive Pythagorean triple. But in this case, C is odd, and exactly one of A and B is even. Well, that's obvious because if C squared is A squared plus B squared, if both of them were even, then C squared would be even, so C would be even. So it would be at odds with, at odds, that was not intentional, with the fact that C is odd. Okay. So assume that B is the one that's even. So assume B is the even one. All right, then there exist relatively prime integers m and n with m strictly less than n, we'll say, so we've labeled them like that. One even and one odd. Such that A is a difference of squares. The next chapter talks about that, although I'm not really going to mention much. I'm probably going to skip it. B is 2 times m times n, and C is the sum of two squares. Okay. So there we go. Okay, so here's some quick examples. If n is 2 and m is 1, then what primitive Pythagorean triple do we get? Then A, B, C is 3, 4, 5. So it's the 3, 4, 5 triple. Right. So here's a question. What n and m give the previous two examples of triples that we generated? So I want you to think about that. All right, so tomorrow I will mention the two main lemmas that are used in the proof of this, but I'm not actually going to prove those lemmas, and I'm not going to prove this theorem either. It would take too long. It's actually a couple pages long. It's actually kind of an annoying thing to. It's not. We already have everything that we need to know to prove this theorem, so it doesn't rely on any advanced machinery or anything. It's just a lot of bookkeeping, and it takes a while. So I'm going to skip the complete proof of this, but I'm going to list out the lemmas that are used to actually show this. Okay, and then we're basically going to, there's a couple of really, really short, like one-page sections next. So differences of squares and prime factorization of factorials. So I'm going to very quickly, I'm not basically even going to mention those. I'm going to skip those directly to talk about the Riemann Zeta function, which is very interesting, and I think everybody will be happy here. So, couldn't A and B both be odd and C be even? Yes, if so. The thing is that would be true were this not a primitive Pythagorean triple. That what you're saying could happen. But for a primitive Pythagorean triple, the C is going to be odd. Okay, so one more thing I was going to say also before I move on from Pythagorean triples is that there's a method that I want to shed some light on that I'm not going to fully do the method, but I'm going to start on it because ultimately my goal for the class is to get to this particular aspect of number theory, which is kind of like I might have mentioned at the beginning. I would like to get to some basic elliptic curve stuff. And there's a way of viewing a question about Pythagorean triples as looking for these solutions with rational coordinates that lie on a curve, in this case a circle. And so we will discuss that a bit later. So I'm going to discuss that in a really, really short way, and then I'll come back to it maybe in like the last week of class. But yeah, tomorrow I will finish out the rest of chapter 5, I think, and start on chapter 6, which has to do with modular arithmetic and congruence, modulo and integer. So that's where stuff is headed. So I didn't post your I'll post your homework here in a second. As soon as I get off here I'll post homework since I forgot to do it yesterday. So anyway. So I think that's all I wanted to say for today, so I will see you all tomorrow.